Welcome to our webinar on setting relays considering FLISR implementation. Thank you for joining us, and we're excited to share some ideas about the fault location, isolation, and service restoration concept that represents one of the most important functions in distribution automation. My name is Gabriela Andrade, and I am a marketing specialist here at Gers. I will be giving a brief introduction, followed by the more technical side of the presentation presented by Dr. Juan Gers. If you have any questions for the Q&A, please send the host a private chat and we will read them at the end of the presentation. So first, I'll give a brief introduction on our company, Gers. Next slide, please. Gers is an electrical engineering consultant group that was established in 1981. To date, we have completed over 6,500 engineering projects and over 3,700 electrical studies in over 45 countries. On this slide, you can see the countries where we have carried out projects from our offices. For this presentation, we will be accompanied by Gers CEO and founder, Dr. Juan Gers. Dr. Gers established his electrical engineering consulting company in 1981, which today has offices in the US, Colombia, Mexico, and Chile. He has a long-standing career in electrical engineering, having worked in academia as a professor at Gonzaga, Penn State, and the Universidad del Valle, in the public sector as the Vice Minister of Mines and Energy of Colombia in 2002, and in the private sector with the Gers companies. He is a published author of several books, including his latest publication, the second edition of Distribution System Analysis and Automation, published by the IET. He is a chartered engineer of the IET, senior member of the IEEE, and chair of the J13 working group of the PSRC of the IEEE. So I'd like to welcome Dr. Juan Gers.
Thank you very much, Gabriela, for your introduction. It is really exciting to be talking about the setting of relays considering FLISR conditions. These days, this topic is extremely important in distribution systems. The way that we will conduct this presentation is divided in these 5 points here, where we will first refer or give a quick introduction to the concepts of system restoration and service reliability, which is the king today. I mean, the service has to have priority above all in the distribution systems. Then we will talk more about the function that we will refer mainly in this presentation, the FLISR, that stands for fault location, isolation, and service restoration. Then we will talk about the 3 types of intelligence that we find today to operate distribution systems, and those are central intelligence, distributed intelligence, and local intelligence. Finally, we will wrap up and have some conclusions about the main topics offered in this presentation. I understand that you guys, the attendants, can formulate your questions in the private chat. So Gabriela will be kind enough to read those questions and discuss them at the end of the presentation. Okay, first, I will refer here to some concepts of power system restoration. Let's say first that the most important points today, I would say, in distribution automation is the service restoration. You know, guys, that there is nothing more annoying than having electrical interruptions. And that is our main topic here. How we recover, how we restore the system following a disturbance or a fault. In order to achieve a good restoration, it is essential these days to operate the switches. There are basically two types. One of them is what we call section switches. Those are the normally closed switches that are associated to a feeder. And of course, those are the switches used to isolate or break the feeder whenever required, mainly for restoration, as we will see. The other type is that of the switches called the normally open switches, also called as tie switches, which are the ones called whenever it is required to transfer loads from faulty feeders into healthy feeders. So the term system reconfiguration or distribution system reconfiguration is basically the operation of section switches and tie switches. I mean, the opening of closed switches and the closing of tie switches in order to recover the distribution system after a fault. That is basically what we will deal today, and we will consider how to do the setting of this type of systems, which of course is becoming a very comprehensive action. Before we start considering the setting characteristics of the protection system, we have to refer to the location of the switches and the way that they are considered. So let me say that the main two objectives when switches are placed in the system are to increase the reliability and the flexibility. In this lecture, we will not devote much time to the location criteria of switches, but we can at least say that these are the two main concerns when locating the switches. Utilities normally, especially in this country, are investing millions of dollars in switches, in protective relays, and of course it is essential to determine how many switches are required and where to locate them in such a way that the reliability of the system is improved. It is difficult, by the way, to say how many switches. There are not specific rules about that. It depends in large on the importance of the loads associated to the different feeders. However, like a rule of thumb, I would say, or I would use a criterion that is used in some European countries, where it is indicated that there should be one switch per megawatt. That means, for example, that if we have a feeder of 5 megawatts, then we can split the feeder in 5 sections. And of course, that would require the connection of 4 switches. Likewise, if we had, let's say, 7 megawatts, then we would require 6 section switches. Now, in regards to the tie switches, or those switches that link two feeders, the idea is to have at least one switch with a neighbor feeder. It is common that sometimes feeders are close in not only one, but several sections. I mean, they can run in parallel. In these cases, again, only one tie switch to join two feeders is the standard or the preference. Of course, that the more switches we have, the more flexible the system is. So it is a very nice topic that, again, we will not deal in this presentation, and that is where the switches are located. And the point basically is to improve flexibility, but above all, to improve reliability. Reliability, of course, is mainly the quality of the electrical service. not referring to the actual electrical signal, I mean frequency, harmonics, etc. Basically, we are referring to the service. And in order to introduce this idea, we normally talk about the quality indices. Outside of the two main quality indices are the SAFE and the SAIDI. But there are many other, I mean, there are like in total 8 quality indices. Utilities also refer a lot to the KD. SAFE is the total number of customer interruptions, basically, divided by the total number of customers served. And SAIDI is the duration of the interruptions. KD is basically the ratio between the SAIDI and the SAFE. Okay, so when we are going to do a calculation, we basically consider the number of users associated to a particular feeder, and then we proceed with the calculation. The application of these formulas is quite straightforward. And a good example, I use that a lot really, is given in the standard 1386 by the IEEE, where you have a typical feeder that has been subjected to several faults in a period of several months. Those are indicated here in this figure. It is interesting to see that some faults, if you see the last column, correspond to momentary faults and other ones to, let's say, sustained fault. What is the difference? It's basically the time. A sustained fault is that which lasts over 1 minute. Most utilities, not only in the US, but also around the world, consider an interruption as a fault that lasts for more than 1 minute. In some cases, utilities can consider a sustained fault that lasting more than 2 minutes, or more than 5 minutes. Now, most indices are referred to sustained faults that last 1 or less than 1 minute. So, if you take, for example, the first fault indicated here, that goes from 12:20 to 12:20:30, it is clear in this case that we have at least from 12:12 to 12:20 at least 8 minutes, and from 20 seconds to 30 seconds, 10 seconds. So this is a sustained fault, of course, because lasts 8 minutes and 10 seconds. While the second fault that happened, say, 4/15, that means April 15th, or these are supposed cases. This lasted or went from 18:23:56 seconds into 18:24:26 seconds. Clearly, this fault took exactly 30 seconds to be cleared, and then we consider this fault a momentary. Why? Because it did last less than 1 minute. And so on and so forth. We don't need to go in detail, but yes, it is essential that we keep track of the reliability indices. So let's say for this feeder that has been subjected to this fault, we can conduct the overall SAIDI and SAFE and KD, for example. I will present here from the same standard, of course, the end result of this. So let's see first the SAFE. So for the first case, we have 200 users. Let me go back for a minute here. I forgot to mention you this. The number of customers affected with this fault, in the first fault, the number was 200 customers. In the second case, we had 400, but this is a momentary, so this doesn't account. In the third case, we had 600 customers, so it does count. Okay, so if you see here, you just take all the sustained faults, here 200, 600, 25, etc., etc. Let me go to my formulation here, and eventually you divide that number of interruptions by the total number of users connected to that feeder. That gives you exactly 1.6 interruptions per year. So this is supposed to be the statistics for 1 year. 1.6. Say the same thing, but in this case you take the duration. So you take the duration times the number of users. Remember that we said that for the first interruption, we know that it took exactly 8 minutes, 10 seconds. Or if you divide 10 seconds divided by 60 seconds that a minute has, I'll give you exactly 0.17. So the interruption took 8.17 minutes, okay, times the 200, and then you keep doing the same thing. I will not go in detail, and eventually you will get for the SAIDI a value of 86.1 minutes per year. Let's analyze briefly these two results. For the SAFE, we got 1.6 interruptions per year. For the SAIDI, we got 86.1 minutes per year. 86.1, if we round the terms, gives, say, 90 minutes, and 90 minutes means 1.5 hours per year. And the SAFE gave 1.6 interruptions per year. You see that most utilities have the target of 1.5 for both. That means 1.5 interruptions per year and 1.5 hours of duration per year. And this example here, of course, gets very close to those figures. You can go to any utility and find this information, and you will see how utilities are embarked in reducing or in improving the quality indices. The KT here, as I said before, is the ratio of the SAIDI divided by SAFE, and that gives you 53.7 minutes. In summary, for us, when we are going to talk about FLISR, basically the main target when we try to implement FLISR is this, to improve reliability indices. So with this brief introduction, then we can go into what FLISR means. Again, FLISR stands for fault location, isolation, and the service restoration. FLISR is the way that it is pronounced, and the simple, I would say, definition is given in the figure that I'm going to present you. We are looking for locate the fault, isolate the fault, and restore the service as soon as possible. So it is better this image than 1,000 words, the saying goes. So let's suppose here that we have 3 substations, A, B, and C. Each one feeds one feeder, and we have, of course, point or a section where they meet. However, the open points are the ones that I am showing here. This dot here, or this switch here, that isolates the feeder from substation A and substation B, and this one here at the bottom that isolates the feeders coming from substation A to substation C. What is the point here? Okay, we will have a fault right here at the very middle. So we will, let's say, assume that the system will first detect the fault, isolate the fault, detect the fault, clear the fault, isolate the fault, and do the system restoration. Okay? Now, when we have the system restoration or the service restoration, mind that normally utilities can first have what is called the upstream restoration. That is the restoration to all those users that were first fed from the feeder. Now, those users that are in other sections of the faulty feeder, but sections which are healthy, could be transferred to healthy feeders of the vicinity. So in this case, let me do the illustration first. We will have the fault. Okay, so if the fault is here, everything goes black within that section, but we will have perhaps the system restoration, what we call again the upstream restoration. So see here, we had the fault. This portion here remains without any power, but the system already reclosed on those users connected to the healthy portion of the faulty feeder. That is called, as it is written here, the upstream restoration. So we had, let's say, with this slide, 3 different actions: fault detection, fault clearing, and fault isolation, and eventually the upstream restoration. Now, we have to do what is called the downstream restoration. And downstream restoration is the transferring of loads or users from the faulty feeder, which are still connected in healthy sections. Of course, where the fault is, we cannot do anything. But in this case here at the bottom, we open this switch here, then we can transfer these loads, these 2 segments here, to substation C, provided that the feeder of substation C has enough capacity, and also if the relay setting is good enough to allow that transfer. Likewise, with the case above, I mean, this section here can be transferred into substation B. Once we do that, then we can see that the healthy portions have been transferred either to substation B or to substation C. There is a section here that remains out of service because the crew has to go there and fix the fault. So that is basically the idea. Of course, the final step in every process like this is the full system restoration that can be only achieved when the crew service fixes the fault. Normally, we would say that there are 5 steps involved in the FLISR, full location isolation and system restoration. 5 steps. The first step, is basically to locate the fault, to find where the fault is. The second one is when we do what we call the fault isolation. So the section involved in the fault is isolated by means of the switches associated to that area. The third one is what we call the upstream restoration. Again, the upstream restoration is the restoration of the users that are connected to the healthy section of the feeder prior to the location of the fault. The last step, the fourth step, is the downstream restoration. That is really the complicated portion because those users have to be connected to neighbor feeders. But in order to achieve this, we have to be extremely careful to make sure that these neighbor feeders will not have trouble when they receive these users. What type of trouble? Okay, number one, we cannot overload them. Number two, we cannot bring harmonics that can create resonance conditions with capacitors, for example, than they have. Number three, they can, for example, exceed the ampacity of the cables, etc. We will discuss this in a bit. So these 5 sections, these 5 steps are indicated here. So again, the number one is that we detect the fault, trip the breaker, and then we locate the fault. And we have in the third step, the upstream restoration. In the fourth step, the downstream restoration. And finally, of course, we normalize the situation once the crew has fixed completely the system, and then it can go back to the normal operating condition. Again, remember that the key here is the quality of service. So I have seen people working in control systems, control centers, trying to do everything in less than 1 minute, if that is the measure for the quality index. The best way to illustrate this is by using a simple example. The example is this one here, okay? Where we will have, let's say, we have here 3 different folds, but we will consider only fold 1. So look here, we have a fold here, okay? We have here different location of switches. In this one, the switches are indicated by this round figure. So between feeders 1 and 2, the best location happened to be this one here, indicated as T1. That means tie line 1. Between feeders 2 and 3, we have this option here. So here we have the tie switch, which normally is open, of course. And between feeders 2 and 3, we have 2 possibilities. The one here shown by the arrow, and this one here we will delocate, which happened to be the best location. As I said, we are not discussing here the criteria to determine location of the switches. So let's have here 3 tie switches. There is a fault here. Remember, there are 5 steps. Step number 1, we just detect the fault and clear the fault by means of the relay installed at the feeder. So the whole feeder goes out of service. These users remain out of service. That is always the first step. Detect the fault. By whom? By the relays. Step number 2, isolate the fault. So we have to know where the fault happened. We have different ways to achieve that. Once we determine that the fault was here, we just open the 2 closest section switches. Section because they were all closed. Third step, once we close this, immediately, without any latency, we can close the breaker here. Because we know that the breaker, the feeder, we know that the feeder can, of course, take this load. Actually, this load will be a lot smaller than the original one. No problem whatsoever. Step 4, downstream restoration. So these users associated to the fault just have to wait till the crew service comes. However, the users associated to section switches 2, 3, and 4 can be transferred either to feeder 2 or to feeder 3 or to a combination. Okay, that's why this becomes so comprehensive. We could, for example, close T1 and then bring all the loads in the healthy section of feeder 1 to feeder 2. Likewise, we could close T3 and then connect all these users of the healthy section of feeder 1 to feeder 3. But by doing so, we can overload those feeders. We can create trouble with voltages. We can create, who knows, trouble with harmonics. Let's say that we might overload them. So the other option is to split these users either by section switches 3 or 4. And for example, we open switch 3. So we transfer only this portion here to feeder 2 and the remainder to feeder 3. It seems simple here in this 3-feeder example. But of course, when we have systems with 200, 300, 400 feeders, of course, the situation is really, really complicated. That makes this very interesting. Okay, another good and simple example. I will only cover 1 or 2 cases. Excuse me. I have here a more clear presentation. Let me tell you that here we have also 3 feeders. We have here the digit 1 that indicates double dead ends. I mean, where we don't have any switch. Remember that the location of switches is quite important. So to connect feeders 1 and 2, let's say we had 3 options. Eventually we picked the 3rd location. So instead of having here a double dead end, we installed a switch, okay? I've said several times that in this lecture, we don't cover the selecting criteria for the switches. But Again, I insist that the two main criteria are flexibility and reliability. Okie dokie, same thing with the other ones. Let's suppose that we have the fault F1. So, question, if we have that fault, the breaker here at substation 1 trips the whole feeder. That is step number one. The second one is to isolate the fault. So how do we isolate the fault? So we open switches 2 and 3. So the faulty section remains only associated to these 4 distribution transformers that I am pointing with my arrow. Step number 3, upstream restoration. Immediately, as soon as I isolate the fault, I close the breaker and feed up to exactly section switch number 2, of course. The fault is actually here. Step number 4. Okay, so these guys between section switches 2 and 3 remain up to service, but the other loads, let's say, can be transferred. So in this case, you can see here that if I close tie 3, I will send all these loads or connect all these loads with the feeder number 3. Simple, but still a very risky condition for the impact that these loads can have in this feeder 3. If we, for example, overload the feeder 3, then eventually the breaker will trip, and in this case, instead of having 1 feeder out of service, we end up having 2. So, system restoration is quite a critical step forward that utilities still have to do. Let me just do other one, the second one, F2. If I have a fault at 2 here, what can I do? First of all, after I clear the fault with my breaker or my relay associated to this substation breaker, the whole feeder remains out to service, and then I open T3, this section 1313, which is the closest to the fault. Once I do that, okay, good enough. I can close this breaker and restore this service. However, I cannot reestablish the service to this user because there is not any possibility. Okay, so again, in this case, my only option is to open the switch 13, but unfortunately, I cannot do what I would call the downstream restoration, only the upstream restoration. For the first case, I achieved first the upstream restoration and then the downstream restoration. Okay, with other cases, similar things happen. This table actually presents exactly what I have explained. You can follow later the other exercises for faults 3, 4, and 5, since you will have this presentation. The thing here is that if we compare the time that we, let's say, require from manual to automatic restoration, or what is called FLISR, of course, the amount of time reduces incredible. In the old days, easily a fault like that could take easily 1 hour, 1 to 2 hours easily. And here, this is a good example that we got where, first of all, after the fault occurs and the customers report that, we could have like 10 minutes. By those days, we wouldn't rely on telephone calls and control centers or locations where communication were kind of limited. And then once the control center was informed about the fault, then they have to have field crews, going to the place with a traveling time, say, of half an hour, and then they should locate the fault. It is not, or it was not like it is today, where we have devices to detect almost instantly where the fault happened, and once the fault was located, so well, they were doing manual switching, and altogether this took, as indicated here, between 45 and 75 minutes typically. Now, this is done at the most in 1 minute and hopefully in few seconds. So this is really the huge advantage. Again, when we are going to do the restoration, especially what we call the downstream restoration, as I told you, there are several things that we have to look after. Now, I will mention here 6 of them, the most important ones. First of all, we have to take care of the current transformers, avoid overloading them, the voltage profile. Remember, when we are in emergency conditions, we can accept lowering the voltage, typically from 0.95 to perhaps 0.92 or even 0.9. But we cannot transfer the loads and end up with a voltage which is 0.75 away. So the voltage drop is essential. The system should be kept radial. Still, you know, we are talking about distribution systems, and they are not meant to work in rings. The other one, we don't want to have so many operations on the switching equipment. So the number of operations should be limited. It is, of course, important to have, let's say, clear the list of the priority users. And priority users, of course, you know, always will have the preference, you know, to restore the service. Those are like, for example, hospitals, of course, police locations, arenas, perhaps academic institutions, and places where there will be a good congregation of people. So important customers have priority, of course. The system, even though it is a distribution system, should be radial. And last but not least, the coordination of the relays, you know, that should be maintained. I put that in red because that is basically what we are talking about. In this lecture, we are caring more about the relays. Let me give you another graphical example, and then we will associate this with protection. We have here 4 feeders, each one coming from a different substation. So we have 4 substations. The first feeder happens to feed like 14 sections. We will assume that each section has the same, let's say, 1 per unit load. So section 1 goes from B1 all the way to switch 4, to switch 12, and to switch 9, which are indicated in red. Okay, this is feeder 1. Feeder 2 goes from breaker 2 all the way to to switch 4. Only 1, 2, 3 sections. Feeder 3 will have 2 sections, 11 and 10. Finally, feeder 4, which is fed from breaker 4, has also 2 sections, 13 and 14. In green, of course, we indicate those switches which are open. In red, those which are closed, as indicated in the conventions here. Okay? So let's assume that a fault will happen here, and we will see the 5 steps that I've mentioned repeatedly. Number 1, the fault is cleared. Number 2, the fault is isolated. Number 3, we have upstream restoration. Number 4, we have downstream restoration, which is the most complicated one, the most critical one. Number 5, we have the total restoration. So I will go quickly into these scenarios. So first we have the fault. So the whole feeder 1 goes out of service because we have the relays at breaker 1. Okay, we don't have relays at the switches, which could be an option, not in this case. Okay, so step 2, we isolate. We locate the fault and isolate it by opening switches 1, 2, and 7. You can see here that the dot point, the red points, in red, the points in red become green. Okay, I go now, there you are. So the fault has been isolated. That is step number 2. Step number 3, we just reclose. I mean, we do the upstream restoration. As you can see here, that is done. That should be done in seconds. Actually, almost, if you will, cycles. Because it's boom, boom. The fault is detected, the breaker operates, the switch is open, and again, the breaker recloses. The fourth one is a complicated one. We cannot transfer these users here to the healthy portions because the fault is here. But we can transfer these two here from feeder 2, this 1, this 1, 2, yes, to feeder 3, and this one, we have here Z8 and Z12 into feeder 4. Now, which goes to where? Well, we don't know. That's where we have to have a proper tool, a proper methodology. This is the tricky point of the case. Let's assume that we can transfer Z12 to feeder 4 and these two sections to feeder 11 and sections 3 and 4 to feeder 2. So we do that. Let me do that in a click. Fine, perfect. So feeder 3 got 2 new sections. Likewise, feeder 4, feeder 1, which started with 14 sections, only will have at the end only 1. And feeder 2 here, I think that got 3 new sections. Good enough. You know, we can feel that this is fine. Eventually the fault is fixed, and then we bring the system back to normal. However, let's go into the protection system. The protection system was operating as indicated here. I already told you. Feeder 1 had 14 sections, feeder 2 had 3 sections, feeder 3 had 2 sections, and likewise feeder 4. But during the downstream restoration, guess what? Well, feeder 1, of course, went from 14 to 1. Perfect, no overload. But feeder 2 went from 3 to 5. Feeder 3 went from 2 to 4, that's twice as much. And feeder 4 went from 2 to 3. In terms of relay pickup, that means that feeder 1, of course, doesn't have any trouble. Of course, if it was handling 14 sections, it can handle without any trouble 1. But feeder 2 went from 3 to 5, that means an increase of 67%. Feeder 3 went from 2 to 4, 100%. And feeder 3 went from 3 to 4. You guys should know that the pickup value of relays, or what we used to call the tap value in the old electromechanical relays, normally is calculated with a security factor or with a overload factor of say 1.3, 1.4, 1.5 times the rated current times the ratio of the CT. Well, if you use 1.5, for example, feeder 1 will have no trouble, but feeder 2 will trip, feeder 3 will trip, and feeder 4 will be at the brink to tripping. So we have to have extra careful when doing the system reconfiguration. And it is there where we have to have extreme care. Okie dokie. So adaptive protection is exactly this. Adaptive protection actually is the technology that considers the possibility of the relays to readjust to the prevailing condition of the system once the operating conditions change. Why? For example, for this case, feeder reconfiguration, or because, say, a PV farm or a wind farm comes into service unexpectedly. I would say unexpectedly because, you know, wind farms can, let's say, close in and out several times in the day, and solar facilities at least 2, early in the morning and early in the evening. So whenever we have, let's say, a feeder reconfiguration, change in topology, or any other major change, the conditions change, and the relay should readjust in order to keep what? The main values that they should cover, like, number 1, reliability. You know, reliability is always, as I said before, the king. Number 2, speed of operation. Number 3, selectivity. Okay? So it is here where adaptive protection comes into place. And basically here, we have to readjust the setting of the relays when the operating condition changes. And of course, the means to achieve that is by using the multiple group setting that most relays have. Most manufacturers these days talk about 4 setting groups at least, normally 6, and we have seen even relays that have up to 8 setting groups. Sure enough, manufacturers will be developing more setting groups. The idea is that the relays readjust to the changes of the power system operating conditions. I will have here a nice example that I like to present, where I have, let's say, one incoming source, that is the grid. We have 2 generating plants. One of them, this could be fossil one, a big one. This could be a renewable source like wind or PV. In this case, anyhow, we have these 5 feeders. Say that this bus bar is at 12.5 kV, fed from this generator and these 2 transformers. Okay? Those 2 transformers are fed from this generating plant, the fossil one, and the grid of the system. And we will consider a simple way to set the relays. So we'll take feeder number 1. Let's say that we will start from scratch here. As you know, what we normally do is, well, we do the calculations of the fault current here to determine the setting of the instantaneous, and we pick the smallest dial available, considering, of course, the call load pickup. So for that very relay number 1, let's suppose that after you apply your criteria to select pickup or tap, you pick the lowest dial, if that is allowed by the call load pickup. Then you, let's say, calculate the fault current by using a software, and with that software you determine that the short circuit current is IF. This is the fault current, and for that typical curve, the time of operation for that relay will be T1. Good enough. Now we will determine the setting for relay 2. Okay, what is the total current that the relay 2 will see if the 2 transformers are connected in parallel? Of course, will be half. So if the current will be half, because the total current splits here, so that current will be IF divided by 2, as we indicate here, 0.5 IF. Still, we need that the relay 2 takes longer time than relay 1, of course, to keep selectivity. So we use the delta time. In the old days, it was 0.5, 0.4 seconds. These days, with the new numerical relays, it could be as low as 0.1, 0.15, 0.2. So let's say that we use the delta time, whichever it is, and the new curve or the curve for relay 2 should go across this dot here, of course. It seems that this relay R2 with the blue curve is somehow slower than relay 1, which is not the case. Actually, that it is faster, excuse me, but it is slower. Why? Because relay 2 sees only half the current. So if the fault happens here, relay 1 should trip in a time of T1, and relay 2 should trip in a time of T2. So, beautiful. T1 is lower than T2 in at least 0.4 seconds, whatever the margin is. Okay? Now, what happens if I take out to service my transformer 2? That is the issue, because the current now will be the same for breakers 2 and 1. The current will reduce a little bit because this parallel no longer exists. So the current will go down, the impedance will go higher. But still, it is not a saying that in this case, this transformer will have the current. No way, because we have the impedance of the source. So let's say that we go to a fraction of that current, say I prime F, which is smaller, not half. And in this case, if we were going to have the operation of the relay number 1, you will see here, of course, that it will be T prime 1 And relay number 2 will be this one here, T prime 2. And in this case, T prime 2 is a lot faster than relay 1, meaning that relay 2 will overlap relay 1, which we cannot accept. No way. So in order to get a proper operation, then we have to consider a different setting group where this relay considers the I prime current, the I prime fault current. And from this point, you can see here that we consider I prime F. We take the operating time of the relay 1, consider the margin in time, and then determine the setting for the second group of relay 2, we call R2A. And you see here that for that condition, the time will be higher than T1 prime. I mean, for this case, we have here T1 prime and T prime 2A is larger as we expected, but we need to have a different setting group for that condition. So whenever we have this transformer out to service or the other one, by means of the logic of the relays that these days they have, they tell the other relay that they are going into a different operating condition, so the relay can change the setting group. That is a typical example of a proper adaptive protection during changing system conditions. Okay, this sounds beautiful. However, today we have systems automated in very different ways. Perhaps you agree with me that there are basically 3 types of automation, what we call the central intelligence, very much used in Europe, distributed intelligence, which is much more used in the States because of the length of the feeders, especially if we go to the northwest or to the Midwest, you know, we will see these very, very long feeders, even in the east or in the southwest. And the local intelligence still is very much used because we still have reclosers. So I will refer to these cases, not with much detail because you should know them, but mainly to indicate what considerations have to be taken into account for setting relays. Okay, so central intelligence. Basically here we rely on a SCADA system, very robust SCADA system that should have, of course, the information of the relays. A good example is this one shown here, taken from Arriva with all the rights. This is a very typical, let's say, nomenclature used in Europe. Here we have, if you see here, 2 main substations. The substation called Robinson has 4 feeders, and likewise here the Bluefield Think substation has also 1, 2, 3, 4. The point is that this magenta or pink color feeder will go out to service for a fault, which will happen here. Okay, so we will see here the same steps again. Number 1, fault location and fault detection and tripping. Number 2, isolation of the fault. Number 3, upstream restoration. Number 4, downstream. Number 5, total normalization. Let's go first to the fault. And you see, once the fault happens, the whole feeder goes from pink to white, meaning that it lost power. Number 2, the fault is isolated, and you will see that the fault was isolated by means of opening this tiny circle here. That is the breaker. So if you see here, the breaker, of course, was here. Originally, the breaker was closed here, because this is the tie breaker, okay? So, still we will, the fault is here. So this is the breaker, excuse me, that has to be open, of course. Now the system already did the upstream restoration, and this is the final point. Where will we connect these other feeders, these other loads, to the, let's say, orange feeder or to the green feeder? We can split them up, or we can transfer all of them. For example, this section here will remain open, but I could close this section here. We could close this breaker and transfer all these transformers, these substations into this one here. Or we could do likewise. No, we could close this one here, you see, and then transfer all these loads into the orange feeder. So the computer, in this case, runs a lot of restoration plans. This is a quite complicated, quite overwhelming number of calculations, and eventually one restoration plan is selected. And you can see here that eventually we split. Some of them are transferred to the green, some of them are transferred to the orange. Still the faulty section remains open. So what is the beauty of this? Well, we have everything controlled from the control center. The control center has all the information of the feeders, and of course, should operate very quickly. But it takes time. I mean, it takes a lot of operations, and these operations should take time. Again, this is the central intelligence. We here in the States perhaps are more prone to use distributed intelligence, where the feeders are divided in sections. Each section should have maximum like 8 switches and work as in teams. I think that this idea came first from our colleagues from S&C, which did a very good implementation on the teams. So instead of controlling everything from a control center, in this case, we have the operation from local teams that talk to each other to determine what switches should be open or should be closed in order to keep the system, let's say, reliable. Again, in order to keep the safety and safety indices in good shape. Now, the local intelligence. The local intelligence would be the simplest one, still very much used. The old concept that we have.
Something went wrong.
I hope that you still can hear me. I was saying that the old technology where reclosers were used in conjunction with section analyzers still exist. In those days, we basically didn't have any communication. Basically, we had these reclosers that would have, of course, relays, and they were working with section analyzers that were counting the number of reclosing operations to do a proper operation. Still that exists, and in many rural areas that is very much used. We can't, let's say, neglect that. This is the final part of my presentation where I have here a real system. The single line perhaps will be a lot clearer. The same system is indicated here, where we have these 2 feeders coming from substations A and B. And we have here, let's say for the first feeder, we have one, let's say, breaker here or switch here, another one serving a section, and we have, let's say, the tie switch here, which is open. Okay. Likewise, for the second feeder fed from substation B, we have basically 2 feeders, excuse me, 2 reclosers, one feeding this section RO5, the other RO4. So I will just show you in a sequence the operation of these devices here, assuming a fault here. You see the settings indicated here for these reclosers, it's 2 and 3 seconds. For this one here, 5 seconds. This is, of course, reclosers, but in here I will have a device that basically monitors voltage. So let's go. We have the fault here, and then of course, once the fault happens here, the red dot should become green to isolate the fault, and it counts exactly 2 seconds. After those 2 seconds, it closes. Since the fault remains, it has another attempt, because we have here 2 attempts at 2 and 3 seconds. So it again counts for 3 seconds, closes, the fault remains, and the system becomes isolated, at least regarding this recloser. Now this counts 5 seconds. As you can see, according to the setting there, it will count 5 seconds, closes, the fault remains, and guess what? It just opens. And then here we can do nothing else than wait for the crew service to come, fix the fault, and then bring the system back to the normal condition. What is the beauty here? That is still the old way to automate circuits exist. And we cannot forget about that. Communication system here is not required, because they just use the proper setting that they have. So basically here we have to consider the central intelligence, the distributed intelligence, and even the local intelligence. And for the 3 of them, we should have a proper relay setting, considering, as I said before, the adaptive technique. These days, we have a special software that can help us to do all these, let's say, considerations. Setting relays is no longer a simple task, because you have to consider different scenarios, pick the most common ones, make sure that for each one of those, you do the proper setting using the adaptive protection technique that we all know. In conclusion, I would mention 4 basic things. First of all, distribution systems are becoming day by day more complicated. Not only because we have distribution automation, but also because we are having more and more the connection of DRs, solar farms, wind farms, which, as I said before, they do not work permanently. So that operation that let's say during the day can be on, and during the night off, of course, impact the current. So the intermittence of that operation, of course, should be taken into account when setting relays. And of course, we are using a lot of FLISR, full location isolation and system restoration based on switches. The switches are essential. We are not vending switches here, but undoubtedly the best way to implement FLISR to improve the indices of safety, and KD is by installing switches. Those switches could have relays or reclosers that have protection, or some could be just monitor or control from the control centers or the distribution centers. But still, we should have different operations to do the proper setting of the relays. And in order to achieve this, the best way, of course, is by using the multiple setting groups that numerical relays in particular these days offer. Now, when we talk about this, of course, the most complicated schemes are those that are monitored or controlled from control centers. The point here is that the overall process, whenever we are setting relays, demand a lot of calculations. It is silly to say, but today it is a lot more costly to do the proper setting, considering different scenarios than the actual value of the relays. Again, in this lecture, we are not going deep into the setting criteria for the relays or the criteria for selecting the location of the switches, but we have just to insist that the methodologies that we have are fine, of course, but should consider different scenarios. And that is, of course, the basic idea of adaptive protection. Well, with this, I don't want to extend anymore. The topic is so hot, so interesting. I would like to do some simulations by using software, but the time is limited. So, Gabriela, I transfer to you the control, and let us know, please, if there is any question. We could take 5 more, 10 more minutes if the audience doesn't mind. Go ahead, Gabriela. Hold on a minute here. Let me see if our coordinator here has perhaps the mic muted. There is something wrong here. I don't hear her. Okay.
Hello, Dr. Gers. Sorry for the technical difficulties. So thank you for the very informative presentation. Now we will begin with the question and answer portion of the webinar. Feel free to send any last-minute questions to the chat, and we will read them out. So we have a few questions here. The first one says, "Thank you very much for the interesting presentation. If a particular distribution system has, say, 100 feeders, how many setting groups would you recommend for this system?"
Well, that is the question that every utility is asking nowadays. And thank you for the question. The answer is very simple. It is impossible at this moment to say that for X number of feeders, Y number of setting groups is required. Normally, what utilities should do is just to determine the feasible operating scenarios and try to associate to each one of them a setting group. Since we have only, let's say, 6 or 8 groups, of course, those numbers shouldn't go beyond that number. However, we will still limit the number of scenarios or the number of setting groups to a feasible number. I mean, we cannot end up with 50. Say, for example, that we have 6 generating plants, and that is the case that I saw in a particular plant, for example. In that case, it is very typical to associate at least 1 group per generating facility. That is for sure. Now, regarding the number of feeder reconfigurations, again, it should go, or it should be based on a thorough analysis of feasible operating conditions. Thank you very much for the question.
All right, we have another question here. If a distribution system has a large number of solar farms or wind generation facilities, and we know that they operate according to the availability of sun or wind, how would you determine the relay setting groups? Okay,
this is also interesting. It is supposed, of course, that the solar facilities will be kind of nearby. So it is customary, perhaps, to associate all of them to one setting group, because they should go on at the same time and off at the same time, late in the evening. Now, for the wind facilities, it is different. If they are also located in the same area, well, we could assume that the wind, more or less, the wind conditions, let's say, would be similar to associate one group of wind farms to one certain group. However, if they are at considerable distances, in that case, the ideal, if those wind facilities are big enough, to associate them to different individual sharing groups. And again, if we are talking about a distribution system, the same reconfiguration possibilities should be considered. So setting groups should be set or should be selected according to the number of solar farms in one hand, wind farms on the other, that could be several, and also possibilities to run the distribution system.
Okay, great. Thank you for the answer. Okay, we have another question here. Would this methodology be appropriate in the case of microgrids?
That's a good point, because normally, well, in the last years, we were more concentrated, I guess, in distribution systems. However, microgrids are coming along very quickly. Actually, we are participating in a research developed by one of our local universities, and that is the point. The answer is yes, still. I mean, for microgrids, unless they are pretty small, yes, we will have, or we could identify several rating scenarios based on the availability of generating plants, normally renewables, different topologies for the distribution system, and do the same thing. I just anticipate that for microgrids, the number of options should be, of course, be a lot lower than for real distributed systems.
Okay, if anyone has any last questions, you can send them in the chat. We did get one comment by Catherine. She says, "Thank you very much for the good presentation." So if there are no other questions, I believe that will be all. So thank you very much, Juan Manuel.
Thank you very much to all. Again, make sure to send your questions either to Gabriela Andrade or to my email that you can see here. I hope these ideas could be good. If you have comments, if you want me to send you more examples, or if you have specific questions, again, we are more than ready to share those ideas. Good afternoon for all, and see you next time. Goodbye.
Okay, also, if anyone is interested in any upcoming webinars, we have one planned for August, September, and October. The registration for these webinars will be found on our social media pages. Also, if the webinar will be recorded and posted on our YouTube, Facebook, and LinkedIn pages, so be free to give it a check. And if you have any questions, you can email Juan Manuel or the email here in the corner, infotech@gersusa.com. Thank you very much.